Yeah.
Well, or at least for me, when I try to open the notes for your day, I get this
Why is it not found? Huh. Let me see. Um, 1 sec. Um, oh. Huh. Da, 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 da. Okay, give it a minute. It's gonna recompile and everything. There we go. Yep. All right. I think we could begin. Um, all right, guys. All right. I think we could begin. The lecture link on the website was broken earlier, but it should be working now, so that's good. I'm also working on actually being able to put the source code onto the onto the onto the GitHub. I have to change a couple things on the website. So I'll do that by the end of this week. Um, I'll do that by the end of this week. So that should be good. Um, so hope everyone had a good weekend. And what did we do last week? Last week we introduced PyTorch. We talked about tensors a lot. Um, and talked about tensors a lot. Then we talked about chain rule derivative sort of computation graphs. But I do feel like towards the end of last week, there we go. Towards the end of last week, especially with the computational graph part, I do feel like I lost a good number of you. So with your permission, I'd like to retread the computation graph, revisit that topic, talk about it a bit more, provide some motivating examples because it is important. It will become relevant, especially next week when we talk about auto differentiation. So we're going to go over computation graphs again, and then we're going to go over some assorted matrix operations. Most of those operations you've seen already, but there's a few nuances that is useful to cover, especially since PyTorch has a habit of Python is a son of Py. I mean, PyTorch is a son of Python, and one of the things Python loves, as a general rule, is abstract away any nuance when it comes to technical issues. And that's especially comes with linear algebra. So I want to sort of go over the nuances of sort of matrix multiplication and why PyTorch will probably try to anticipate what you want and sort of forgive you if you make some notational issues, which isn't a bad thing if you're a very experienced mathematician and you know what you're doing. It's not a bad thing, but if you're a student trying to learn, it's not the best thing in the world. That's one of the reasons that why you shouldn't, I'm a firm believer that Python should never be someone's first programming language. The first programming language you should learn is C, because it doesn't forgive you. Then, once you know how to program, then you could go to a language that is forgiving. But anyway, that's a whole other thing. Okay, so let's go back to computation graphs, and let's just establish some motivation for what we're going to learn this week, because I know, it's a hard thing to learn sort of a fundamental math or science topic, and that is seemingly disconnected from the overall goal, the overall objective that you have. So let's go over what the overall objective is, and why what we're learning this week is necessary in order for us to get to that overall objective. Okay, so let's think of the deep neural network. I'm just going to say, let's think of the deep neural network we commonly see in literature. For instance, in the case of image classification, for AlexNet, the task is that you're given a particular image that's made up of pixels. Each of those pixels is multiplied by a weight, goes into some activation function. Then that information is passed on to a new layer, which is passed on to a new layer, and which is passed on to a new layer, and which is passed on to a new layer, and eventually you get to the end, the last layer of the network that gives you its confidence on, is this image a dog, or is it a car, or is it a flower, et cetera, right? If you remember, the ImageNet data set had about 10 categories, which included these sorts of things, right? So this is sort of where we want to get to, right? By the end of this course, well, we want to get a little further we want to get substantially further than this by the end of this course. But by the midsection of this course, this is where we want to get to, right? We want to be able to program this network very quickly and efficiently, right? So we have this model, and it's randomly activated. It has a whole bunch of weights that you don't know beforehand what those weights should be. Your model, let's assume, is not pre-trained yet. And so you just initialize it randomly. You get some outputs out. And for instance, in this case, your model tells you that it thinks this image is a car, which is obviously wrong, right? So what do? You have a particular ground truth. You know what your model should be outputting, which is it should be outputting a 0 for a car and a 1 for dog. That's because we know this is for sure a dog, right? So we have this ground truth, and we have what the model is outputting. And we know that the model is wrong, so we have to adjust the model in some way so that it better matches whatever ground truth we have for this example. And this is true for every other example we go on to. Okay? So what do? Well, we say that what's the change in the last layer that we need to get from what the model is producing now to what the model should be producing. So we analyze this and say, somehow that changed. We analyze this and say that, okay, we need to adjust the model so that this last layer, this value increases because it's supposed to be 1, and this value decreases because it's supposed to be 0, and so on, right? So we know how the change in the last layer should be, but the question is, how do we get there? Because we have all these weights that all sort of interconnect and build off each other to get to the value in this last layer. So we simply say, okay, the change in this last layer needs to be -0.9. And so if we look at this neuron individually, we see that, for instance, in order to get to this value to be -0.9 using some derivative calculus, we could calculate out that, okay, in order for this change to be significantly impacted, we need to change this weight to increase, we need to change this weight to increase, we need to change this weight to decrease, and so on and so forth. Okay? And then from there, we sort of go back through the network and say, okay, we need these weights to increase or decrease in order to get these values where they need to be, and so on, right? So that's what we want to be able to do. We basically want to be able to adjust the network so that the output is equal to some sort of ground truth. We want to minimize the difference between what the model is currently doing and what the model should be doing. And we do that by analyzing the change at the output. And we're trying to figure out if the change at the output needs to be this much, then what should the change at the layer before the output be? Then what should the change for the layer before that be? And so on and so forth, right? So that's our motivation, okay? All we're trying to do is adjust a complex function in order to better match some sort of ground truth for training. And then, of course, we evaluate how well we train the model with a test or verification set. Okay? Does that make sense? All right. So then the question is, how do we do this automatically? Okay? How could we do this automatically? I mean, it's possible to not do this automatically, right? Famously, AlexNet, there was no PyTorch for AlexNet, so famously, you wrote your own auto differentiation function, and literally you had to write the structure of the network using default Python, or I mean not default Python, like NumPy, and then you sort of you calculated the derivatives and programmed them in by hand, and then you backpropagated the derivatives manually, right? So that's great. You could do this manually, quote unquote manually, i.e. by creating a model and by analyzing the function, the actual activation function, from the beginning to the end for each layer of the model. You could do that. But we're learning about PyTorch, and PyTorch is all about automation, that you won't have to do this. So PyTorch abstracts away the process of manually understanding each function, each intermediate function in the network by computation graphs. So that's why computation graphs are so important, is because PyTorch is going to convert this to a computation graph so that when you backpropagate, when you want to make sure the output is adjusted by so much, then PyTorch will understand, okay, in order to adjust this, then I need to adjust this by this much, then I need to adjust this by that much, and so on and so forth, okay? So literally, we have to reconstruct the computation in the forward way and in the backward way. That's the idea behind a computation graph. Okay, so in order to do that, we're not going to go for the complex network right off the bat. Let's go over hello world network first, okay? And let's first consider the network we talked about in last lecture, or the computation, the function that we talked about in last lecture. Namely, we have a composite function that is made up of 3 separate functions, and this composite function is simply the sine of log of x squared plus 1. And we know that this function here is the composite of these 3 individual functions, okay? So we could rewrite this function f of x as k of h of g of x, okay? So why is this important? It's because basically this is allowing us to separate out the computation into distinct steps, because it's very difficult to get the derivative of this whole function right off the bat. But we could break this derivative up into d of f. Oops, there we go. We could break the derivative up. There we go. Should have put a slide break there. But we could break the derivative d of f of x into d of k dk of h times dh of g times dh of g times dg of x, and multiply those three together to get the total gradient at the output. Okay? So let's look at an example. We have this, let's look at the actual code that helps us do this. We have okay, I'm going to use okay, let me go back to the slide. Oops, not there. Come on. Okay. Let me go back to here. Okay, so we have this network. We have this network right here. Okay? Now, for a value of x, let's say x is equal to 1. Let's say x is equal to 1, y is equal to some value. Okay? Now, what we want in this network has no inputs. What we want to do is something similar to this network, right? We have a particular output we get from the network, but we have a particular ground truth that we want to get, okay? So for this network here, let's say the ground truth of this network is that we want this network to simply output y equals to 0, okay? X is just some parameter in the network. It's not an input, it's just some parameter in the network. The network has only a single parameter, and that parameter is x, and and our ground truth is y has to equal 0. Okay? So we want to be able to figure out what value of x, what value does x need to be in order for y to be equal to 0. Does that make sense? So there are a couple ways to do this, of course. We could literally, oops, there we go. We could literally set f of x equal to 0. And we could set f of x equal to 0 and then solve all of this. Take the inverse cosine, then raise to the exponential, the square root of that, or minus 1 times, then the square root of that. We could literally just set f of x equals 0 and solve directly that way. Or we could do the machine learning approach, which is we set the output to 0, we set x to some value, we calculate what the network gives us at that value, then we calculate the difference between what the network is giving us versus what we want, 0, and then we adjust x up or down based on the derivative at the output in order to get closer to 0. And if we do that a couple times, hopefully we get approximately the value of x, what x should be in order for y equal to 0. Does that make sense, what we're doing? So that's the difference between machine learning and sort of analytic mathematics. Analytic mathematics, we would just set this to equal to 0, and we would solve directly for 0 that way. And those of you that are clever, I know that you see what x should be already in order for y to be 0. I mean, it's a simple example. But let's say we're not clever. I'm not very clever. I don't know. I didn't see immediately what x should be. So I'm just going to set x to be some value. I'm going to just set it to be 1. I'm going to look to see what that function is equal to. And then I'm going to adjust x up or down based on the value of f, based on the value of y, and the gradient at the output. Okay? So that is literally how PyTorch works. We define a function here, and we set x to be some particular value. In this case, we're setting x to be, x is a torch tensor, and we're just setting it to be a scalar that's equal to 1. Okay? But we are also telling the machine, and we're going to tell the machine, and we're going to go over this in a moment, we're telling the machine that we're going to require that it keeps track of x, and it keeps track of all the functions that are built off x, because we're going to want to do backpropagation in a minute. Okay? We're going to go over that. But that's what that required grades is. Okay? And this optimizer is simply what a function that will adjust x so that y gets closer and closer to 0. Okay? Literally, what optimizer does is that whatever value you give it, it basically tries to adjust the parameters so that the function, so that the output becomes 0. So in next lecture, we're going to say that in this case, we want y to be equal to 0. So that's why we don't really need to do anything right now. In next week, we're going to discuss, okay, maybe instead of y equal to 0, we want the difference between what the model predicts and what the ground truth is equal to 0, right? That's another way to use optimizer, okay? We're just trying to make the difference between the current output and the ground truth output equal to 0. So that's what an optimizer does. It just tries to force the output of a function equal to 0. Okay? So we initialize this optimizer. We zero all the gradients. We set y is equal to this composite function here. And so after a first step, we see x is equal to 0, x is equal to 1, and y, there we go. Actually, could I do that? No, I can't. I had it right originally. Okay, I'm just gonna have to. Sorry, my Firefox, there we go. So at the first iteration, x is equal to 1, y is equal to 0.638691 something, and we know that dy dx is equal to some value, 0.76939239, okay? And we know that this is true because we can manually calculate the gradient as we did before in the previous slide. And when we manually calculate the gradient, we get the same value. Okay? That's a good sanity check. Okay? So with this information, x is initially 1. Y is some value greater than 0. And the gradient is positive. What do we do with that information? Well, we tell ourselves, okay, if x is equal to 1, and the gradient is positive, and y is greater than 0, greater than where we want to get it, we want to lessen y. So if the dy dx is positive and we want it less than y, what do? We have to lessen x, right? We have to make x smaller. So that's what the optimizer does here. Next step, the optimizer simply sets x is equal to 0.9, and again, calculates y. We're getting closer to 0. Y is now at 0.55. And the automatic gradient of x is still positive. It's 0.82, greater now, but that doesn't really matter. It doesn't really matter what the derivative is. All that matters is that this value is telling us in order to make y smaller, dy dx smaller, then all we need to do is make x smaller also, right? So next iteration, that's what the optimizer does. Instead of 0.9, it now makes x 0.8. And then y, again, decreases the value, gets closer to 0. Y is now at 0.47. We're getting closer. And again, the gradient is roughly the same. So the gradient is roughly the same, and it's positive. So again, we tell ourselves we need to make x smaller. Then we make x at 0.7. Y gets smaller. Then the optimizer makes x 0.6. Y gets smaller, and we do a couple iterations until we sort of settle on. We do a couple iterations, and maybe I should have done more than 10 iterations. There we go. I'll do 20. We do a couple iterations until x gets close to, until y gets pretty much close to 0. Okay? And then, if we're not careful with the optimizer, x could go off the rails also. X could go too small and into the negatives, and then we would have we would have a function that we're not enthused with. But then y would increase, and then it will slowly decrease back. Okay, so we'll get into the nuances of why that happens. It's a stochastic operation, so why that happens. But the point of all of this is that we just want y to be equal to 0. So we take a random value for x. We calculate the gradient at that random value. And in this case, if it's positive, then the optimizer tells itself, OK, in order for a positive value of y to get closer to 0, we need to make y smaller. And if dy dx is positive, then we need to make x smaller. So we'll then make x smaller and restart the whole thing again and again. OK? Does that make sense? OK. So this is the essence. Come on. Stay on page. Okay, let's try this again. There we go. Okay, so this is the essence of gradient descent, and we're going to be going over gradient descent in more detail with more complex examples next week. But this is the idea behind it. This is what we want to do, right? So the question is, this model of PyTorch, all the information that we gave it is this function. We didn't really give it much information about the network itself. We just said y is equal to this composite function, and it's equal to this composite function, and we want to perform a backward propagation from y to the value to x. Okay? So how did PyTorch figure all of this out? How did PyTorch figure out how to calculate the gradient of y at x? That's the question here. That's the point of all this exercise. So it did that. There we go. It did that by using computation graphs. And if you guys want to go into more PyTorch internal details, I highly recommend the PyTorch blog or this guy Easy Yang. He's a big contributor to PyTorch, and he writes a lot of blog posts about how PyTorch works under the hood. So I highly recommend that. But how do we create the computation graphs? That's the question. So let's start off. Let's start off from the beginning, where we told PyTorch to initialize a new tensor x and to require the gradient equal to true. Okay, so doing this tells Torch, okay, we have a new tensor 1 that will be involved in a gradient calculation. So what does this mean? It means that it allocates a structure to store a particular graph. Okay, and it allocates a structure to store a particular graph, even though that graph doesn't contain much. It's much yet, only the tensor that requires the gradients. But it creates an autograd meta object that can store the graph information and where new nodes of the graph can be added to it. Okay, so we start off with this blank graph, or almost blank graph. We start off with the tensors, with the leaf tensors that require the gradients. And then we go on and we start adding functions to our tensors, right? We start putting functions on top of the tensors. So the first function we put on top of the tensor is that composite function g of x, okay? So if we initialize g of x, and I did this just because PyTorch, when you tell it g equals to x squared plus 1, it has a it basically allocates multiple nodes in the graph because x squared plus 1, there are multiple operations in that phrase. So that's why I broke it up there. But when we define a function on top of a tensor that's requiring a gradient, what PyTorch is doing is it's allocating a new tensor. Okay, it's allocating a new tensor, and it's allocating a gradient function depending on what the operation you defined is. So as you see, for g1 equal to x squared, it allocates a new tensor that's literally a single value, and the gradient function it allocates is called power backward. Okay, so what does this mean? In PyTorch, so all of PyTorch is written with C, by the way. So that's why you'll have to go through YAML files. But the idea here is that every time you define a function here, PyTorch looks at this function, it inserts some extra code, and basically says, every time I see this function, every time I see a function that's a power function, I'm going to add in a new node here, a pointer to a new node. That's literally the derivative of the power function. Okay, so that's what's happening here. It's literally, so that's what's happening here. You're adding in a tensor, so you are adding in G here. This is the tensor G, but you're also adding a pointer to a new function, which is literally just the derivative of whatever operation G performs. Okay, and how these operations are defined is basically there's a preset file, and you could look it up. There's a preset file under tools autograd derivatives.yaml. YAML file is just like, I mean, you guys have seen it. It's just sort of it's a data file. It's this data format, right? Literally in this file is basically most functions, most activation functions that we could possibly see. You know, addition, subtraction, multiplication, a whole bunch of arithmetic operations, sine, cosine, trig, all the transcendental functions, a lot of common neural network functions like ReLU, sigmoid, all those functions are in there, and literally all this file does is define the derivatives to these functions. Okay. Very simple. It's a bit of a manual process, but given that people have been contributing to it for almost a decade, well, not almost a decade, two-thirds of a decade, it's a substantial file, right? So this file literally defines all possible, well, not all possible, most possible derivatives of functions that you'll use in your network. And if you don't, and if there is a function, if you come up with some weird, very weird, you know, what do I say? If you come up with a function that someone hasn't added to the YAML file yet, you could actually define your own derivative for that function, and PyTorch will add a pointer to that, just like it is, right? But the major point of this is that you add the computation graphs, looks at this function, it sees x requires gradient, so that flag is raised. So it says, okay, I'm going to create a new node G in the computation graph that is related to x, to that leaf through this computation. And I'm going to actually have a point, I'm going to add a new node, dg, and I'm going to change this leaf to dg dx. And the operation between dg versus dg dx is the derivative of this computation here. Okay? That's all it's doing. So you go through this. So you add a new composite function. So you add a new function on top of x, and it adds new nodes to the computation graph. Okay? So same thing when we define the log function. Now we say h is the log of g. So what does that mean? Well, you define a new tensor, and the gradient function is literally called log backwards. That makes sense. All you do is define add new nodes to the forward direction to say h is the log of g. Awesome. But you also add new node in the backward direction and a new function in the backward direction. The log backwards in the backward direction, which would simply be 1 over the value. Okay? And all of this is defined in the YAML file. And same thing with sine. You have you define a new tensor, okay? And you define a new backwards function, cosine, okay? So doing all of this allows you to calculate the actual backwards gradient of dg dk dx by simply following dk dx from dk to dk dx. Okay? So it uses this computation graph to actually calculate the gradient of dk dx. Okay? So that's all this is doing. So that's how it. So that is how it helps. So that's how PyTorch keeps track of the computation from x to any value that is built off of x. Every time you create a new tensor that performs an operation on a tensor that either has the required gradient flag set to true or the gradient function flag set to something, then it creates a new tensor with a new gradient function flag based off the operation that you do. Okay? Does that make sense? So that's the concept. So that's the conceptual idea behind computation graphs, that you're just keeping track of the order of operations. And so, if we look again to the TensorBoard utility that we had before, that we created before, we could initialize it the same way that we did before. Oh, using this piece of code. Again, the syntax is slightly different because we have to use torch.nn modules. It's the same idea, just different syntax. I don't know why they do this. Well, I know why. It's because like multiple libraries got merged, and so you have multiple syntaxes that are. You don't want to ever. No one wants to upset anyone. So whenever someone's already used to a piece of syntax, like it's sort of legacy software, people add it to the software, and then you're left with like a whole bunch of different syntaxes. But anyway. So in this case, as mentioned before, if you got the TensorBoard utility, you could define a torch.nn module, which is literally you're defining the network. Again, g is equal to x squared plus 1. The log, and h is equal to the log of g, and k is equal to the sine of h. And you define the network. And so you could do the same back propagation with this network that we did earlier. But in our case right now, I just want to show you the graph. So you could use this little function, add graph. You could initialize the input to whatever. So in this case, we just want an input of 1, input shape of 1, a single scalar value. And then if we write that to our file, we could open up the TensorBoard utility. You could open up the TensorBoard utility using that command, and it'll show you something like this, that we have a network that goes from a single value, x, and then it is of dimension 1. And then what happens at this particular node, let me see if, there we go. At this particular node, we see that the operation at this node is a power operation, and the value of this node here is simply 2. So what is this telling us? It says x goes into a node that's the power of 2. I don't know why it's not letting me zoom. I think it's messing with it. The projector screen is messing with it. Okay, I'll just do this. Yeah, perfect. So x goes in, so x is a scalar, size 1. It goes into a power operation of 2. That makes sense. That's literally what we defined here. Power operation 2. Then G1 goes into an addition. That takes in 1. That takes in 1, and it adds it to 1. Then we got h, that is a log function. Then we got k, that is a sine function. And then you get the output. Then you reach the output. Okay? Makes sense, right? So PyTorch is keeping track of all of the computation from x to any other tensor built upon x. Okay? Make sense? So I want to posit something for you guys. I was working on this the other night, and I see G. Oh, man. Python, Firefox is not being nice to me today. Sorry. CG, and it's addition, right? That makes sense. That makes sense. And G takes in G1. That also makes sense. That's one of the additions. That makes sense. It's the power. G, so x squared. G takes in x squared. Makes sense. And then you add 1. Oh, man. I'm going to use, oh, this is Chrome. I'm going to use, or is it Chrome? Is it? I'm going to use Firefox next time. You've let me down, Google. So G addition, and so it takes in a 1 over there. That makes sense. We're adding x squared to 1. Okay? All is kosher there. Then, if we look here, there's an extra 1. Well, there's a tensor 1. That's the x squared plus 1. And then there's an extra 1 right here. All right? It's not a tensor. It's a value. But it is there. What is that? Any ideas? How would we actually try to figure out what this is? Why are there 3 inputs to the add node right there? Yeah.
Well, one of them is probably the 1, right?
One of them is 1, yeah. So we have one of them is x squared, which makes sense. One of them is the 1. That also makes sense. So what's the other one? There's 2 1s going into that node. And I don't expect you guys to necessarily know what it is, but I mean, it would be great if you do. But I'm wondering what you guys would do in this case. Yes?
Well, one thing that stands out to me is the value is kind of like a dictionary in quotes. So that makes me think it's kind of like a metadata that's stored somewhere.
Could be.
Like the value of s over there is the string, curly brace value colon 1.
Right, right. Could be. So it is, yeah, so it is, so this comes into how you would define metadata. I think you're right. You're right if you define metadata as something that's not explicitly defined. That's not explicitly defined. So there is something there. So there is like some parameter or something that we didn't define right here when we did this plus 1. There is some parameter that we weren't explicitly defined, but it is there, right? So I'm telling you guys this just to get you into the habit. You look at this, you see add. So this is literally the torch.add function. So you could literally go to torch.add here and look at the actual documentation. And then you notice, oh, there are more than 2 inputs. There's the input, there's other. And then there's this alpha input that coincidentally is implicitly equal to 1. And what alpha is just alpha is just a way to scale the second operand of add in a computationally efficient manner. So it was a bit of a mystery. I had to work it out a bit, but I wanted to share it with you guys because you're going to come up with things that supposedly don't make sense, like for instance, add taking in 3 parameters. So the best thing to do, instead of wondering, instead of Googling and all of that, just go straight to the documentation and you'll probably see immediately why that is. Yeah? Okay. Okay, so that was fun. Okay, so is everyone satisfied with that? Any questions there? No? Okay. So computation graphs. So I hope that this convinces you that PyTorch, hope this convinces you that actually computing the computation and computing the derivative is actually a very simple thing for PyTorch to do. It's very algorithmically simple. All PyTorch is doing is that whenever you define something like G1, it's literally saying, hey, this tensor has a required grads flag, so I have to write in a little bit of extra code that in the computation graph, in addition to adding G1 into the forward pass, I'm going to add d of G1 dx into the backward pass also. And then once you have this computation graph here, once you have a computation graph like this, it becomes trivial to calculate the gradient of at any point in the network dx or d whatever parameter. Okay? And we're going to go over that in more detail with more complex networks next week. Okay? But it's just important to sort of understand the motivation and have some footing on what we're trying to do. Okay. And as mentioned, literally how PyTorches work is that it's actually inserting extra code in order to calculate the computation. So the Easy Yang blog post that I linked to earlier, that goes into that detail on how it's adding that extra code very well, a lot better than I could go into it. So feel free to read that. Okay. Live tensor board matter. Okay, so now I think we've beaten this horse. It's near death. So the question is, we understand the ins and outs of some simple network, basically a no-input network where there's only one parameter, and we're trying to optimize it so that output is equal to 0. We understand how that works for the most part, but we need to get from this one value, one scalar value that goes through, admittedly a complex function, a complex series of functions, but still it only has one scalar value, to something that has hundreds, thousands, millions, billions, etc., a number of parameters, okay? And how we optimize those, okay? So how do we get from this to this? Well, we get to it with matrices and linear algebra, okay? So that's what we're going to start on today, and that's where we're going to end next lecture. Make sense to everyone? All right, so linear algebra, most of you, I believe, have taken 275, Math 275, so I won't belabor any of these points too much, but please feel free to ask questions. But as we mentioned before, a scalar is a single number. A vector is a one-dimensional list of numbers. Matrix is a two-dimensional list of numbers. And a tensor is an n-dimensional list of numbers. And in fact, one of the things I like about this graph is that a good way to visualize it, vector, one-dimensional, two-dimensional, three-dimensional. And when you go to greater dimensions, like four-dimensional, it's good to visualize this as multiple three-dimensional matrices. Multiple three-dimensional tensors. And in fact, with the tensors of rank 3, you could visualize the tensor of rank 3 as multiple two-dimensional matrices. Okay, makes sense? Anyway, I think that's a good way I like to think of it that way, so hopefully it helps someone else. So we refer to anything that has 3 or more dimensions as a tensor over a matrix. all that makes sense. We went over that, I believe, last week. So, as far as fundamental operations of matrices go, the transpose of a matrix is found by switching its rows with its columns. So we have a particular matrix here, A1, so m rows and n columns. So the transpose of that matrix is literally n rows and m columns. Okay? So we could do in PyTorch, as we discussed last week, we could transpose a matrix in two ways, using torch.t or torch.transpose, and defining the actual dimensions. So if we use torch.t, we just simply switch the dimensions. So a 2 by 3 matrix becomes a 3 by 2 matrix. That makes sense. And if we do matrix transpose and actually say that we want dimension 0 transpose with dimension 1, it does the same thing. Okay, literally the same thing. And again, we went over sort of this function does not work well. Why setting the actual dimensions is important. Remember that if you're dealing with larger than 2 dimensions, you have to use transpose and set the actual dimensions, versus if you're dealing with this dot t only works with matrices of 2 dimensions or fewer. Hopefully you remember that. The dot product, the inner dot product of 2 vectors is simply a single number, a scalar, and it's calculated by multiplying the corresponding elements in each vector and adding up all of these products. And adding all of these up. So for instance, 1, 2, 3 times 4, 5, 6 is equal to 1 times 4 plus 2 times 5 plus 3 times 6 and 32. Okay? So a good way I like to think of it is that PyTorch is effectively doing the transposing for you in a lot of these operations, right? So this is literally the matrix multiplication if we're multiplying a column vector by a row vector, right? So that I prefer to think of it because it stops me from making minor errors. But it also is much harder because you end up debugging for hours when you forget to transpose something. PyTorch takes care of a lot of that for you and basically says that, okay, if we want the dot product of 2 vectors, we don't have to make sure one is a column, one is a row, or whatever. It's just 2 vectors. We know, just take the element, just multiply each element and add them all together and get a scalar. Makes sense? Yeah, so code, if we have 2 tensors of the above, we get some scalar 32. Okay? Okay, and the operation is commutative, of course, because it's just multiplying 2 values together. Multiplication is commutative, addition is commutative, therefore the dot product is also commutative. Okay. And you can prove this by simply multiplying b times a, verifying. Okay. And so, let me ask you guys, what happens if the vectors are not the same size? What do you guys think happens? Yeah. Does the 0 pad one of them? Oh, that would be interesting. No, simpler than that. Simpler than that. It just throws the error. Yeah. I know. Why would I ask such a simple question? And the answer is, why not? Yeah. I don't try to trick anyone. So yeah, if there are 2 things, it's just undefined, right? So yeah. So and it tells you literally right there. If we read the error, inconsistent tensor size, expected tensor 2 and source 3 to have the same number of elements, but 2 and 3 elements respectively, but got 2 and 3 elements respectively. Good error. Good error message. If only I actually read my errors before going nuts. Okay. Okay, matrix vector dot products. So we multiply. I mean, again, this is similar to just matrix, 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 matrix. Similar to matrix, matrix multiplication. There we go. You could effectively just imagine this as a matrix, as the matrix getting multiplied by a matrix of m by n getting multiplied by a matrix of n by 1. And then you would get, of course, a single 1D size m vector that way. Okay? But in PyTorch, there is a special function called torch matrix vector multiplication that just calculates the dot products of a 2D matrix with a vector, and to give you that. Okay. So again, we have a matrix of size of 2 rows times of shape 2 by 3, and we have a matrix of vector of size 3, and of course the matrix vector dot product is size 2 long. Okay, and notice here that the shapes, it's not like this where you have to, where the vector has to be a column vector. Over here, it's just a single row. It's just a single row. Again, PyTorch figures out sort of the dimensionality aspect of it and returns back a single row vector as well. Okay. A single a single vector as well. I shouldn't say row vector, just a column vector. It's just a vector. Make sense? I think that makes sense. And of course, this is the same exact thing as if we did the matrix multiplication of A times B. Literally, remember this @ symbol? I keep forgetting what this symbol is called. What's this symbol called, the @ symbol? Does anyone know the formal name? No? Oh, what is it called? Oh, I always call it that. There is a name for it. I'll look it up later. This @ symbol literally says matrix multiplication and does the exact same thing as torch.mv. So why even have torch.mv? Oh, and by the way, the @ symbol, remember, the @ symbol is literally just a way to say torch.mm. So this is matrix multiply. This is matrix vector multiply. And literally, they do the same thing. Like, you get the same output if you use either. So why does matrix vector multiply even exist? What do you guys think? Yeah.
There's some kind of optimization you can do when you know that the
Yeah. No. Perfect. Oh, you got it way faster than I did. I spent a lot of time looking at this. So yeah, there's an optimization. Basically, you have a little bit of additional code, namely that the second quote-unquote matrix is actually a vector. So we could actually test this out. And if we actually test out the two functions, the time taken by matrix vector multiply is significantly less. What is this? Like almost 20% less than the time taken by matrix multiply. Not orders of magnitude, but it is significant, right? Could be the difference in days if your training time takes a significant amount of time, right? Yeah, perfect. Yeah, so that's a real good rule of thumb, and I'm glad you guys have already picked up on it. If there are two functions that do almost exactly the same thing, and it's not apparent why one function exists when you have another more general function that does pretty much the exact same thing, the reason is almost always speed. And so if you really want, you could go in and try to figure out the algorithm behind it. Although that's a lot of work. I just accept the fact that it takes, I just test case and accept the fact that it's faster and move on. Okay. So Hadamard product is probably one of the few matrix operations you probably haven't seen yet. So in contrast to matrix multiply, Hadamard product is sort of a combination between matrix, is sort of a dot multiplication for multi-dimensional matrices. Namely, if two matrices have the exact same shape, you just multiply each of the elements within that matrix to get a new matrix of the same shape. Okay? And so this comes in useful for a variety of neural networks, as you can imagine, especially when you're calculating the weight matrices times the input. Yeah, yeah, so resulting matrix is of the same order. So again, this is just the code to the above. We have a 2 by 2 matrix with the Hadamard product of another 2 by 2 matrix, and we get a third 2 by 2 matrix as a result. 1 times 5, 2 times 6, 5, 12, yeah, etc. Okay, and kind of interesting is that, remember, matrix multiply is the at symbol. The Hadamard product is literally the multiply symbol, which personally I find confusing, but it is. But PyTorch is built for non-mathematicians, so that nowhere is it more evidence than here. Yeah, so at symbol is matrix multiply, true multiplication. Time symbol for matrices is Hadamard product, and for vectors, it's the Hadamard product also. But instead, with vectors, you get a single. No, for vectors, it's not the Hadamard product. For vectors, it's not the Hadamard product. It's only the dot product. Sorry. Okay. Actually, wait a minute. Now, as I'm saying this, is there a difference between if I do the vectors like this? Let me see. Let's see something real quick. Do we get the Hadamard product if we times it, or print A times B? I think we get the Hadamard product. A times B. Yeah, we get the Hadamard product of vectors. Okay, good. That makes sense. So time symbol, Hadamard product, at symbol, matrix product, MV, matrix vector multiplication, torch dot multiplication with vectors. Okay, all that. You guys able to have all that memorized? Keep it in your head immediately. So yeah, dot product of two matrices requires the dot product of two matrices is literally the matrix multiplication. So again, it requires matrices to have a certain shape, basically for left operand to have equal columns to the number of rows in the right operand. Okay, matrix multiplication. So we've seen that. So torch at M is the dot product. Yeah. I do wonder. See, as I'm saying this, does it allow me to do torch dot A comma B? Oh, no, it doesn't. Okay, so torch dot is for 1D vectors, and torch .mm is for matrices of any shape. Okay. Okay. All right. So that's all good. Yeah, and of course the dimensions matter. So for instance, a 2 by 3 times 3 by 2 matrix. So this row gets multiplied by this column. This row gets multiplied by this column, and etc. That will output a 2 by 2 matrix, but a 3 by 2 times 2 by 3 matrix will output a 3 by 3 matrix. Okay? So you guys know the 2D matrix multiplication rules. I don't think we need to go over that too much. And of course, matrix multiplication, as we showed before, is not commutative because A dot B is not equal to B dot A, and so you have to be careful how you do the dot products. Yeah, so showed that. And of course, what happens if the dimensions don't match? We get a nice little runtime error that says the shapes cannot be multiplied, namely since both of these matrices have the shape 3 by 2, this value and this value are supposed to be equal, but they're not, so therefore it gives you a runtime error. Oh, that makes sense, right? Okay, so we have a bunch of different functions to multiply two tensors, and when we have the option, we should of course use .mv or .mm because they give us because there are runtime operations. Because runtime-wise, it could be faster, right? But there is a general torch.mat-mul that computes the multiplication of two matrices or vectors or a mixed match between the two. And given what you enter into it, for instance, if you give torch.mat-mul two two vectors, then the scalar product is calculated. Again, this is the dot product. If you give it two matrices that are both two-dimensional, the general matrix multiplication is done. If you give it a vector in a matrix, the tensor 1 is prepended with a value to match the dimensions of tensor 2, and then everything is multiplied that way. And if you give it a matrix multiplied by a vector, again, the torch.mv is calculated, although not as fast. And then if you give it larger dimensional matrices, what happens? Well, remember the image before that a four-dimensional vector matrix is like literally could be considered a collection of three-dimensional matrices. A three-dimensional matrix could be considered a collection of two-dimensional matrices. So this is very useful because if you want to batch your matrix multiplications, right? If you want to perform a bunch of matrix multiplications, multiply a bunch of different matrices, but at the same time, you could do some interesting operations. For instance, over here, you could batch multiply. Scalar. So you could batch multiply those matrices together. So going over, two vectors multiplied together gives you a scalar. Matrix times two matrices multiplied together gives you the matrix multiplication. Vector times matrix gives you vector times matrix multiplication. And same thing here. And matrices that are multidimensional. So for instance, this is a three-dimensional matrix times a vector. Then what happens is that this vector is multiplied by each of these matrices, like so. Okay? So all this is called is a batched matrix multiply. Okay? So big thing of this is that you're going to be pretty much with your networks, you're going to be pretty much using two or one-dimensional matrices. And so when you see something like this, that's three-dimensional, what's happening is likely batching. You're trying to collect a bunch of matrices and do a bunch of the same type of multiplication together. Okay? And so you're going to see more of that later in the semester when we discuss batching in neural networks. Make sense? Okay. Okay. So yeah. So I think we've gone over a lot of the basic matrix operations. You guys have seen it before last week. So next time we're gonna go over how to use matrices for linear algebra, systems of linear algebra, and also sort of eigenvalues, eigendecomposition, some more advanced linear algebra stuff. Okay. And then we'll be ready for auto differentiation. So have a good day. Enjoy the weather. I'll see you on Thursday.